Deep in our galaxy sits an object suffering from a severe split personality. One moment, it behaves like a silent ticking metronome in the dark. The next, it erupts with blinding bursts of chaotic energy. These eruptions are terrifyingly powerful. If you placed this star a sixth of the way to the moon, roughly 40,000 miles from us, its magnetic field would instantly wipe the data from every credit card on the planet. For years, we thought dead stars followed a strict set of rules. On one side, we have pulsars, rapidly spinning remnants that emit steady, predictable beams of radio waves, like a cosmic lighthouse. On the other side are magnetars. These are rare and rotate much more slowly, but they possess magnetic fields of 1,000,000 billion Gauss. This intense energy triggers violent, erratic outbursts of X-rays. In March 2020, the Swift Space Telescope spotted a massive X-ray flare 15,000 light-years away. It looked like a standard magnetar outburst, and the source was cataloged as Swift J1818. But when radio telescopes turned toward this violently bursting star, they found something impossible: the steady, ticking radio pulses of a pulsar. These two behaviors were thought to be mutually exclusive. By exhibiting both at once, this single object defies our entire taxonomy of the graveyard of stars. Understanding this split personality requires looking at the exact moment a massive star's core collapses inward before exploding violently into a cloud of debris. In late 2024, researchers observed a supernova named SN 2024 AFAV. Inside the explosion, they found direct evidence of a newborn magnetar spinning wildly, completing a full rotation every 4.2 milliseconds. The supernova emitted a strange, accelerating signal that researchers compared to a bird's chirp. This led them to Einstein's general theory of relativity, specifically an effect called lens-Thirring precession. As the magnetar spins, it physically drags the fabric of spacetime along with it. This dragging forces a tilted disk of falling debris to wobble. As the disk moves inward and spins faster, it periodically blocks the star's light, creating flashes that arrive closer and closer together to produce that chirping signal. This violent birth proves that young magnetars start their lives as wildly spinning, chaotic engines. They are inherently unstable from the moment they are forged. Swift J1818 is essentially the survivor of that violent birth. At roughly 240 years old, it is a baby magnetar, the youngest ever found in our galaxy. It retains the rapid spin of a pulsar, rotating once every 1.36 seconds. This speed is what drives its steady radio emissions. This chart tracks the evolution of J1818's radio pulses. Looking at the line graphs in the top row, you can see how the star physically shifts between 4 distinct emission modes, with the profile changing over months of observation. This high-resolution X-ray view highlights the magnetar side of its personality. The bright central point is the result of a messy, misaligned magnetic field, creating a violently active surface. This top panel shows the star's spin-down rate. Its rotation doesn't slow down smoothly. It fluctuates erratically, like a damped harmonic oscillator, with the zigzagging fluctuations gradually shrinking in magnitude as the star settles. The twisting and snapping of these messy magnetic loops act as a physical switch. When the magnetic configuration shifts, the star flips, erupting into a magnetar outburst or settling back into its pulsar state. The dual behaviors seen in Swift J1818 identify it as a critical transitional phase in the life of a dead star. Astronomers call this the buried field theory. It suggests that J1818 began its life as an ordinary pulsar, with its true power hidden from view. During the initial supernova, massive amounts of stellar debris fell back onto the young neutron star, physically burying its immense magnetic field beneath the surface. Over hundreds of years, that buried field slowly forces its way back to the surface. When it finally breaches the exterior, it triggers the violent magnetar outbursts we detected in 2020. This wide-field view shows J1818 as a small blue source within the crowded active plane of our galaxy, surrounded by the debris and nebulae that shaped its early years. If magnetars emerge from buried fields, then the distinct properties of pulsars and magnetars may simply be snapshots of the same evolutionary path. This star serves as the missing link, showing how one population can eventually transition into the other. This discovery redefines our view of the night sky. It isn't a gallery of static objects, but a living ecosystem where even the most violent remnants are just enduring a chaotic cosmic adolescence.